Can somebody help us about the molecular formula of butane? Butane is C4H10. Of course, when you look at this butane, the molecular weight of this butane will be 4 times 12. That is 48, right? 48 plus 10. That will be 58 is the molecular. That is butane. When you look at 2-methyl propane, it is an isomer of butane. 2-methyl propane means the straight chain compound are 3 carbon. 1, 2, 3. And there's a 4th carbon that is a branch on the position 2. You see CH3 here. This first carbon, we need how many hydrogen to complete? You know, carbon is tetravalent in nature. It has already bonded with 1 bond to the second carbon. It will need 3 other hydrogen to balance the 4, right? This last carbon is only 1. It has used 1 bond to bond with this. To be tetravalent, it will need 3 more hydrogen, right? This middle one already has 3 bonds. 1 to the left, 1 to the right, and 1 downward. How many will it need more to complete its tetravalent? 1.
1.
That's how to fill hydrogen on your structure of organic compound. So this is position 1, position 2, position 3. This is 2-methyl. There's a methyl group in position 2, and the longest carbon chain here is 3. 2-methyl propane. So in this 2-methyl propane, if you look at it very well, it has 1, 2, 3, 4. 4 carbon. And also, if you count the hydrogen, it's 10 hydrogen. So the molecular mass of it is also 58. But what are we now trying to say? The weight of this is 58. The weight of this is 58. You cannot use molecular weight to say this one will melt faster than the other, or this one will boil faster than the other. But the degree of branching is showing that this butane has 4 carbon long straight chain. You call it N-butane because it's normal butane means it has straight chain throughout. But if you come to the second one, it is 2-methyl propane. Which one of them will have a higher melting or boiling point? N-butane or 2-methyl propane? Can somebody help us?
N-butane.
N-butane, we ask what? A higher boiling point, right?
Yes, sir.
Very good. That's the thing we are talking here when we say the straight chain compound will have a higher melting and boiling point than their branch chain isomers. I hope we get that. So let's look at a practical question. C8H18. If all the 8 carbon are straight chain and is 8 carbon, we call it N-octane. And you can now have 8 carbon that have high degree of branching, 3 degree of branching. Let's say out of the 8, only 5 are straight chain. Only 5 are straight chain. There is 1 branch as number 6. There's 1 branch as number 7. And there's 1 branch as number 8. Now, which of these 2 8 carbon systems will have a higher boiling point? N-octane or this branch chain isomer?
N-octane.
Very good, because N-octane has 8 carbon straight chain.
Yeah.
Even though both of them are C8H18, you cannot use their weight to distinguish which one will have a higher. But the branch chain here, we have a very low boiling point than the straight chain. This is what happens when you are increasing the octane rating for you to get a petrol that will burn at a very low temperature. You see, this N-octane has 8 carbon, 18 hydrogen. This isomer has 8 carbon, 18 hydrogen. But if you are using this N-octane as your petrol, before you start your ignition, the temperature that will be needed for it to boil and go and impact your engine with capacity power, will have burned the driver on the driver's seat. So what now happens is that they now did isomerization of this straight chain and turn it to the branch chain, and you discover that even without adding fire, when you open petrol in a broad daylight, you see the vapor of it going, boiling on its own. This is what happened. CHH18 is the carbon content that we call petrol. But the one we call petrol has a very low boiling point because it's an isomerized octane, which is this. So this has 5 carbon straight chain, 1, 2, 3, 4, 5. And on position 2 of it has a methyl. On another position 2 of it has a methyl. On another position 4 of it has a methyl. So this second isomer that is having high level isomerization is called 2, 2, 4 trimethyl, because there are 3 methyl now, plus 5 straight chain carbon, making 8. Trimethyl pentane. So this 2,2,4 trimethyl pentane is an isomer of N-octane, but that will have a very low boiling point required for internal combustion engine to be powered by petrol. Your petrol you are using on your car is this compound, 2,2,4 trimethyl pentane. So when you are trying to change N-octane from a straight chain form to this isomer form, you are doing isomerization to get a better octane rated petrol. Because N-octane cannot work because the temperature needed for it to impart strength onto your engine will be extremely high than what even the driver can cope with. These are practical application of what we are saying. Then when you look at 2 isomers, that one is a trans isomer and one is a chain, is a cis isomer. You see there also that there is this thing. Let's look at the example of that. When you are talking about cis and trans isomer, of course, you must have known that there's a double bond. Let's look at this. If there are methyl group on the same side of this double bond plane, then you have a cis isomer. How many hydrogen will this carbon take? Remember, I've told you carbon is tetravalent in nature. It has 1 bond here, 2nd bond here, 3rd bond to the methyl. How many more does it need?
3.
How many more does this carbon need? It's 4 that is complete tetravalent, Abby. Now it has 1 bond here. It has the 2nd bond here. It has a 3rd bond here. How many more bonds does it need?
1.
1. Good. This is 1 will now be the hydrogen. This carbon, how many bonds will it need more?
1.
1. Very good. So when you see this compound is having, when you see that compound is having the 2 bulky methyl group below the plane, this is what is called a cis isomer. This is what we call a cis isomer.
Okay.
Now, if I'm sorry, let me just quickly save this thing. Okay, so when we have that cis isomer, what that is telling us is this. Let's look at how many carbon that are there. This is 1, 2, 3, and 4. This is both 2N. It has 4 carbon is both, and it has double bond on position 2 is both 2N. Is both 2N. Because the 2 bulky things that attach to your carbon-carbon double bond are on the same side of the plane of this double bond. This is what is called cis both 2N. It is also possible that both 2N can have another stereochemistry in which the bulky methyl group is below the plane on the carbon here, and the bulky methyl group is above the plane on the carbon here. When that happens, it is still both 2N, but it is called a trans both 2N. This is trans, because there's a transportation network because before those two methyl group can feel effect of each other. This, we need to cross this road before you can feel this guy. So these two are both two in, but this is a cis isomer, this is a trans isomer. Because the bulky group are well spaced out on the trans isomer, it has a better stability than the cis isomer where they're already confronting each other because they are both sharing below the plane. So in such case, the highly stable compound will withstand higher temperature than the less stable compound. So we are saying the trans isomer will generally have a higher temperature at which it will melt compared to the cis isomer. So if I say 2 bottles of but 2 in was given to you, one is suspected to be trans but 2 in, and the other one is suspected to be cis but 2 in. And I'll now ask you, how can you help me to identify which one of them is trans but 2 in and which one of them is cis but 2 in? What will you do? Yeah, the first bottle is but 2
Please,
in.
can you repeat the question?
I said there are 2 bottles. Let's call it bottle A and bottle B. One of these bottles has trans but 2 in. One of these bottles has cis but 2 in. And the label of their name was removed by mistake, and they handed it over to you. They are now saying, please help us to identify which one of these is trans but 2 in and which one of them is cis but 2 in. What will you do?
So check the melting points of both
Very
of them.
good. If they are solid, you check the melting point of both of them. If they are liquid, you check the boiling point of both of them.
Boiling
After
point.
changing that, how will you now justify what is what? Let's say
I think
one of them. Yes.
The cis but 2 in has a lower boiling point.
Very good.
Trans
That's all.
in
That's
has
all. That's all what I want to hear. So if they give you those 2 bottles and they say one is cis and one is trans, but we don't know which one is cis, please can you help us to know? You go and do the boiling point. If the boiling point of the A is 60 and the boiling point of B is 95, you'll know automatically that B contains trans but 2 in. So you label it and give them. Why A contains cis but 2 in? Because it has a lower boiling point. These are ways to use boiling points and melting points to justify the identity of compounds. And you can see some of the curve of the molecular things when you are increasing the carbon atom by odd number and by even number. That of even number is a little bit higher than that of odd number, according to that curve. And then the another thing is, of course, the boiling point is like the melting point. The only difference thing is that in the boiling point is liquid that is applicable to. The temperature at which liquid boils and turns to vapor is called boiling point. The temperature at which solid melts and turns to liquid is called melting point. So you can also define boiling point as the temperature or the point at which the vapor pressure of the compound is equal to the atmospheric pressure or external pressure from the environment. So there will come a time when you are boiling something that the pressure of what you are boiling in the pot is counter-equal to the external pressure. That's when that thing reaches boiling point. So the vapor pressures of the compound in the pot, when it's equal to the external pressure, then that compound boils. So you used to know the compound identity and also the purity like the melting point. So factors affecting boiling point are many. One is molecular structure. If something has molecular structure in which the entity of the molecule are regularly arranged in a well-packed together form, it will be more stable and therefore have higher boiling point. But if something is haphazardly arranged, just like the Brownian motion, then you know that the high level of disorganization will cause the increase in the entropy and therefore make it to boil faster. Another thing is that a molecular weight, a compound that have a higher molecular weight, you expect it to boil at a higher temperature than a compound that have molecular weight that is low. Another thing is about the degree of branching. The higher the degree of branching, the lower the boiling point of your compound, because as compound enjoys degree of branching, then you see that the point of its melting begin to change. Let's look, for example, at what we have here. Polarity of bond and the molecule also increases the boiling point of the compound. Let's look at 3 isomers that have the same molecular weight. So you cannot use molecular weight to justify them here. So let's see N-pentane. N-pentane is C5H12. Is C5H12. 1, 2, 3, 4, 5. That's C5H12. If you look at isopentane, 4 of those carbon are straight chain, 1, 2, 3, 4. The 5th one is a degree of branching. So isopentane has 1 degree of branching as compared to N-pentane. And then neopentane has 2 degrees of branching as compared to pentane. But all of them are C5H12. They will have the same molecular formula all through. But because there is no degree of branching in pentane, we call it N-pentane. It boils at 36.1. Now, when you come to the other pentane, which is isopentane, because of 1 degree of branching, the boiling point lowers from 36 to 27.9. And when you come to neopentane, which is 2,2-dimethylpropane, 3 carbon straight chain, 2 carbon degree of branching, it is still 5 carbon. See, it dropped far from 36.1 to 9.5. And this is to show that the degree of branching, the higher the degree of branching, the lower the boiling point of compound, the molecular weight notwithstanding. Another parameter is solubility. Of course, solubility is governed by a law of likes dissolves likes. Likes dissolves like. Something that is polar solid will dissolve easily in a polar solvent. Something that is a non-polar solid will dissolve easily in a non-polar solvent. Like for example, if you look at sodium chloride, is a polar solid. If you look at water, it's a polar solvent because you know O and H has high electronegativity difference that leads to charge formation between them. So when you add sodium chloride to water, it dissolves readily. But hexane is non-polar. You know, it's C6H12. It's C6H14. Hexane is non-polar. So if you add sodium chloride to it, stir it from today to tomorrow, it cannot dissolve. Heat it on fire from today to tomorrow, it cannot dissolve. Why? Because the hexane is non-polar solvent and the sodium chloride is a polar solid. But if you look at candle is a solid and it's a non-polar solid. Okay? And hexane is liquid and it's a non-polar liquid. If you add candle even to hexane or petrol or to kerosene, it will melt and give you solution. So what we are trying to say is that any compound that have a polar molecule attached to them, example of polar molecule is OH, hydroxy group, sulfonic group, carboxylic group. Any compound that have that attached to them, they are polar. And then they can relate with water or with polar solutes in such a way that is friendly for them to dissolve. If you look at the structures of what we are trying to propose here, we are looking at a solid compound that is XY, YZ. The Y part of it is positively partial, and the Z aspect of it is positively partial. The water is a liquid. What will happen is that water begin to crowd around that solid in such a way that the negative part of the water coming from the oxygen will begin to align itself close to the positive side of that solid, which is Y+. While the hydrogen that is positively charged in the water will begin to align itself with the negative charge, which is Z-. And of course, when the positive and negative come, they will attract each other. So this is how the water molecule will begin to crowd itself around the molecule of your solid until it embedded itself in it by attraction and therefore begin to leach it out to dissolve that compound. That's why when you put the sodium chloride in water, you see the white particle there. But as you are stirring it, you begin to see more of the molecule of water entering into the sodium chloride bond. And therefore, you begin to see that solid disappearing until there's no more sodium chloride solid. So that's about this. So these are the example of table of the boiling and the melting point to let you know that as the number of molecular weight is increasing, the boiling point is increasing. In fact, for every CH2 increase, there is always a regular pattern of melting point that you can even predict. If you look at CH4, which is methane, and C2H6, which is ethane, it's as if it's as a result of adding CH2 to methane that you get ethane. If you add CH2 to ethane, you get propane. If you have CH2 to propane, you get butane. And if you look at that carefully, the range of their boiling point has a steady increase of that format, even including their melting points too. That even with that, you can even predict what are the boiling points of the next one. Class activity 1. Let's try this. 3 bottles labeled as A, B, C has the boiling point of their content to be 79 for that A, 90 for that B, and 98.24 for that C. Using the knowledge of your degree of branching, correctly assign this content to these 3 compounds: 2-methylhexane, N-heptane, and 2,2-dimethylpentane. Can somebody help us? Can somebody help us out? Which of these 3 compounds will be compound A with the melting point of 79? Which one of them will be compound B with the melting point of 90? And which one of them will be compound C with the melting point of 98.2?
Compound A. Compound A will have a melting point of 90.
I've told
And
you
that would
A.
be
Wait. Let me just re-explain myself because of exam. When you hear the word respectively, it means the first thing you mention is the owner of the first parameter you have.
Okay.
The second thing you mention is the owner of second parameter you have. And the third thing you mentioned is the owner of the third parameter you have. That's the meaning of that respectively. The bottle label A means that it has the melting point of boiling point of 79. Bottle B has the boiling point of 90. And bottle C has the boiling point of 98. That is settled. That's not where the problem to be solved is. But where we are now saying is that each of these compounds we mentioned below will either be A or B or C. We are saying that A is 79. Which of 2-methylhexane, N-heptane, and 2,2-dimethylpentane, which of them will be A that have boiling point of 79? Which one of these compounds will be B that have the boiling point of 90? And which of them will be C that have the boiling point of 98? That's what I'm asking.
So the A, the one with the 79 degrees Celsius, would be 2,2-dimethylpentane.
Okay.
Then B.
So hold on. Somebody is giving us that this compound is our A. Okay. Yes.
Then B which is 90 degrees Celsius, is 2-methylhexane.
Yes. Somebody is saying this is B. Okay.
Then C, which is the last one with 98.24, will be N-heptane.
Very good. Can you justify why you assigned this?
Because normally, like before, you said the one with like the long chain has the highest boiling or melting point.
Okay.
And N-heptane, it has like a straight chain,
Okay.
like a which
when,
is
when you say N-heptane, how many carbon do you have there? Hept. When you add the word hept, you need to go and learn this thing. No?
7 carbon.
7 carbon, very good.
7 carbon, yes.
Yeah, 7 carbon.
Yeah, 7 carbon.
So very good. I agree with you totally for what you did. It's very correct. It's very correct. But just for everyone to have understanding, that's why we are trying to do this. N-heptane means there are 7 carbon, and all those 7 carbon are straight chain. 1, 2, 3, 4, 5, 6, 7. That is N-heptane. Okay. Now, 2-methylhexane. It means there are 6 carbon that are straight chain, and 1 carbon is a branch chain.
Yes.
Yes, it is still this 7 carbon. 1, 2, 3, 4, 5, 6, and then on position 2, there's a branch. It's still 7, but with 1 degree of branching. 6 straight chain and 1 degree of branching. Then the third one, pentane, means 5. You have 1, 2, 3, 4, 5. Then on position 2 of it, there is a methyl group up. On position 2 of each two, there is a methyl group down.
Methyl group down.
So you can see
then
that
by
it
the
is
last one,
all of them are 7 carbon and 16 hydrogen. So you cannot change the molecular weight to justify, because C7H16 will always have the molecular weight. But what you look here carefully is the degree of branching. I was just trying to help you when I say using the degree of branching. If I keep quiet without saying this, you should still be able to know that, even though all of them have 7 carbon, this is an N-heptane. It must have the highest boiling point, and that will be 98 degrees, which is compound C. And this one has 1 degree of branching, C straight chain, and 1 degree of branching. It will be the middle point. That is compound B with melting boiling point of 90. And this one, of course, has 2 degree of branching, 5 straight chain carbon, and 2 degree of branching to make up 7. And therefore, it should be the lowest boiling compound. That's good. So we're about to round up on that. So yes, you are correct. Thank you very much. That's a very good one. So you are correct. Okay. So number 2, solid compound X, Y, and Z were reported to have melting point of 200 to 209, 127 to 130 degree, and 155 to 156 degree, respectively. Hear that word again, respectively. It means that the melting point of X is 200 to 209. Name melting point of Y is 127 to 130. And melting point of Z is 155 to 156. Comment on the purity level of this compound. Can somebody else help us? Okay, somebody is raising their hand, please. Go ahead. What do you want to say? You have lowered your hand again. Please, let's go to our question. Number 2. So, who can comment on the purity level of these compounds?
Okay. Compound Z has a higher purity level.
You said?
Compound Z is more purer than compound X and Y.
Why? Why is compound Z is more pure, is the purest?
Because if you look at the range of their melting points.
Okay.
Compound Z has a smaller range.
Very good. Very good. 1 degree range difference.
Yes.
So when you want to know the purity level, is not how big the value is. Don't say, this one is 200. Why can't we say it's more pure? Each compound have its own unique boiling or melting point. That does not affect their purity. What affects their purity is it started melting at so and finished melting at so. What is the range? So 155 to 156 is 1 degree range. 127 to 130 is 3 degree range. 200 to 209 is 9 degree range. Therefore, the purest compound is Z with the melting point of 155. While the one that has highest impurity level is compound X with the melting point of 200 to 209. Note very well, it's not because it's having value of 200, that's why you have the highest impurity. The reason why you have the highest impurity is that it started melting at 200 and finished melting at 209. So the melting range is 209 minus 200. That is 9. 9 is quite big. 3 for 127 to 130 is a bit pure, but not as pure as Z. That's very good. So I think our time is fast fetched and we still have a lot of things to cover. This is the essence of instructing us to go and look at the PowerPoints and also watch the video so that our 1 hour we can use it judiciously for the area of concerns to us. So I think at this point, it's a convenient place for us to draw the curtain for today. Don't let us forget, our topic 2 for week 2 will be done 7 p.m. next week, Saturday, by God's grace, or this week, Saturday coming. And our week 2-3, topic 3 will be done normally on Sunday by 7 p.m.
Okay. So that means we have class on Saturday and Sunday.
Yes, because last week we did not do our class. Waiting for people took our time and people did not stick up. So, but I've agreed, I've summoned the courage that no matter what, even if it's only 1 person that comes, our facilitation must go on. That's why we are now trying to create a time for Saturday to cover up for the 1 week loss.
So about what time is the class?
I said that on Saturday is an extra class we all agreed to have by 7 p.m. 7 to 8 p.m.,
Okay.
just like this time now. 7 to 8 p.m., we use it to cover what we have lost. Then our Sunday, we still hold as our normal class, which is 7 to 8 p.m. on Sunday. Then after this week, there will only be Sunday class throughout the facilitation. So this Saturday is just a class arranged to just cover for last week omission.
Okay, sir, but it's 7 to 8 on Saturday also, right?
Yeah, 7 to 8, everything, so that you don't forget his time. The only difference is that one is Saturday, one is Sunday, 7 to 8 p.m. And I will have sent the link of the YouTube to watch and the PowerPoint to you. I've already shown you how to get information on your course page.
Yes,
If
sir.
you scroll it down, yes.
I want you to, can you please say something about the melting point? The melting point, like in boiling point, you said that the branching in chain decreases the boiling point, and further branching in chain also decreases the boiling point further. But in melting point, I saw that branching in chain decreases the the melting point. Then further branching in chain increases the melting point again. Please, can you explain that?
Where did you see that one?
I saw that in our course material when I was studying the course material. So they wrote a structure, N-pentane, the normal pentane, then 2-methylbutane, then the 2,2-dimethylpropane. So they put
both for the melting and the boiling point, the parameter are the same. The normal straight chain, we have a higher melting and boiling point. See the normal pentane now, 5-carbon straight chain has a boiling point of 36.1. But when there's a degree of branching where we have 4-carbon straight chain and 1 branching, it is still 5-carbon. But by the reason of this degree of branching, the melting point, the boiling point dropped from 36 to 27. And when we go further to the higher degree of branching, where we have 2 degrees of branching, 3-carbon straight chain, 4th carbon degree of branching, 5th carbon degree of branching, it's still lower from 27 to 9.5. So we are saying the degree of branching, the higher the degree of branching, the lower the boiling point, and the higher the degree of branching, also the lower the melting point. But the only difference between them is that melting point is applicable to the solid because it's the temperature at which solid turns to liquid. While boiling point is applicable when you are dealing with liquid substance because it's the temperature at which the liquid boils and turns to gases or vapor. Are we clear?
Yes, okay. Could it be that what they wrote in the course material is a mistake?
What did they write? What they wrote, was it different from what I'm showing you here?
It's different from what...
Then it's not this one that you are talking. Maybe it's another one. Because there's a place also that there's an explanation that when your degree of branching cause a better stability to come on board, is not a normal regular thing, but it's thing that can occur once in a while. When the degree of branching led to something much more stable, the higher the stability of a compound, the more the capacity to withstand higher temperature when you are adding temperature to it. So that's what they are trying to use to explain that one, that in some condition, if the degree of branching has led to having a compound that is much more stable, symmetrically speaking, then it will confer an abnormal high melting or boiling point on it. So it's a special case. I think they will have it in one material, in course material. It's a special case. So thank you very much.
I understand.